Okay, I was going to go to bed, but I'm so excited about these. I'm going to do one more before sacking in for the night. This is a famous classic problem, which is maybe of special interest to college students. Because if you ever have gone to college where you lived in the dorm and then you wanted to build your own loft in your dorm room, then you basically need to pull all this plywood down the hallway and get it into your room. So I don't know if this has ever been a problem for a dorm in a dorm room, but sometimes you're interested in, or you might be interested in, what's the longest board that you can get around a corner of a hallway from a hallway of, say, width A to a hallway of width B. Okay? If A and B were the same size, then it's easy because there's a symmetry there, and you can figure out what's the longest board. I'm gonna draw it larger right here for the moment. This particular problem is going to take a lot of room, so I need to keep everything small. But anyway. If they were the same size, then it's basically a 45-degree angle, and you just find the longest board that goes kind of like this along here and up to there. So first of all, notice that we're assuming that the board has infinite thinness. So there's no thickness to the board. Also, we're not lifting it up to the ceiling. It's you can think of it like a needle, a really heavy needle that you're sliding along the ground if you want to. And it's an optimization problem. It's a max-min problem, obviously, because we're trying to find the longest board. But interestingly, it's not finding the maximum, it's finding the minimum. Because just think of what's going on here. What you're really doing is, you've got this board like this, which you always want to butt up against the corner, and you want it to be able to get around this corner. So if you think about it, you might have a board that's whatever, 100 feet long, and you're going down this hallway, and as you go down this hallway, you put it up against this wall right here, and you slide it this way as much as possible. I tell you what, let me make this a little bit thinner just so that I can illustrate it a little bit better. Okay, so here it is right there. Notice it's butt up against this hallway wall, and this one as well. And now it starts off at 100 feet, and when you get it up here, you just keep shaving it off. You just keep shaving it off. Whoops, it's too long again. Whoops, it's too long. See that? It's right here. So it's too long, so I keep shaving it, shaving it, shaving it. And you keep shaving it until you finally get it around, the crucial angle. Once it gets around enough, then it can be as long as you want again. But what you're really doing is you're finding the minimum of all of these possible distances, because all these possible distances of this line right here, whatever all those are, just think of them all. This one here would be really long. This one here would be really long. Okay, but whatever the shortest of these is, that would be the longest board that you can get around that corner. So it's really a minimization problem to give us the longest board. It's really kind of interesting. And I told you that I have something to do with this problem because this has been in calculus books for years and years. It's classic. But the problem that it's always been in calc books has always had numbers here, 8 and 12, for example, or 8 and 9, or 8 and 10, whatever. And then you use a calculator with an inverse tangent or something like that in order to get, some decimal answer. And I got thinking, this is back when I was a grad student, well, what if you don't know what if these are just, some numbers there? Can you get an answer in terms of A and B without resorting to the use of a calculator? And I figured it out. And I've given it to some authors, and now it appears in textbooks as well. So anyways, I'm kind of proud of this particular one. So anyway, let's do it. So let's think of it like this, that you've got this board here, and the length of the board is L, and L depends on what this angle is. So let's let this angle here be theta. Okay? Yeah, that shows up. Okay, so that's theta. And so this angle here would also be theta. Okay? And so now we can, well, this is actually, it doesn't follow quite all the steps of the standard problem that I gave you. We can basically find L in terms of theta right from the start. That's the easiest way to do it. So let's do it like this. Well, I tell you what, let's call this x right here, and let's call this y right there. So this distance from there to there is x, and from there to there is y. So if we want to, we can say that L of theta is equal to x plus y. But now we have to determine what x and y are. So let's do it. So that's easy enough. Look at this. Here's where we are. We see that, what's the relationship? A over x is the sine of theta. Everyone agreed? A over x is equal to the sine of theta. And we want to solve that for x. And so if you go up here, you're going to get x is equal to A over the sine of theta. So that's what x is. Okay? And similarly, what about y? Y is this distance right here. And b is this distance right, let's see, b is this distance right here. From there to there, that's b. And so this angle, what do we have? We have that the adjacent over the hypotenuse is the cosine of theta. So b over y is equal to the cosine of theta. So if you solve it for y, you get y is equal to b over cosine of theta. So we can write that right there. So now, as I say, for sake of room, we're going to have to get rid of this stuff after having explained it. So there it is. So that's the length as a function of theta. And now we want to know, when is that length going to be a minimum? And notice it's obviously a minimum that we're getting because, as I explained earlier, for some values of theta it's going to be infinitely long this way, and for other values of theta it's going to be infinitely long this way. So we're going to find that one in between where, for a particular value of theta, that's a minimum. And that's going to be, of course, where the derivative is 0. So let's go ahead. Take the derivative. See what we get. So here's L prime of theta. And a and b are constants. And so what do? We take the derivative of the top, which is 0, times the bottom, minus the top, times the derivative of the bottom, all over the bottom squared. See that? Same thing here. Derivative of the top, which is 0, times the bottom, minus the top, times the derivative of the bottom. Derivative of cosine is minus the sine, all over the bottom squared. Okay? So now we set that equal to 0. And if we set it equal to 0, I'm just going to, again, just for sake of space, I'm going to just make this all one equation, set it equal to 0. And now I can bring this over to the other side, and I get, well, basically, how about this? Can I save even a little more room? If I bring this over to the other side, it's going to become, well, I'll fill that in. I can do that. So it's going to be what? A cosine theta all over sine squared theta is going to be equal to b sine theta all over cosine squared theta. Agreed? So, so now let's see, what can we do? Let's go ahead and bring sine squared up here, and divide both sides by cosine. And so we're going to end up with sine cubed of theta all over cosine cubed theta. Sine cubed over cosine cubed, and let's bring the b down there, is equal to a over b. Okay? Which means that this is the tangent cubed, which means that the tangent of theta is equal to the cube root of a over b. And the cube root of a over b I can write as the cube root of a divided by the cube root of b. Okay? So this is where in the standard textbook you would you'd have your a and your b there, and you'd have some number here, and then you would take the arctangent of each of those and find your theta. And once you took the arctangent and found your theta, then you would plug that in to sine and cosine, and you'd get your length. So that's the way it could be done. The question is, how can we get this knowing only this? And the trick is that we never have to even know what theta is. It's enough just to know what tangent is. From tangent, we'll be able to find sine and cosine. So remember what I taught you back in the trig section, I think it was, or was it a little bit afterwards? I can't remember now. But we did this. We said suppose you have an angle. I don't even need to make the whole unit circle. Suppose you have an angle whose tangent, here's the angle right there, whose tangent is this. What's the easiest way to make an angle whose tangent is this? Well, the easiest way would be to make this on this side and this one on this side. Agreed? The tangent of this angle is the cube root of a over the cube root of b. Now that we have the angle whose tangent is this, we can find the sine and the cosine of that angle. How do we find the sine and the cosine? Well, we use Pythagorean's theorem. What does Pythagorean's theorem say? It says it's the square root of the sum of the squares. The square of this thing is a to the 2/3 power, and the square of this thing is b to the 2/3 power. Agreed? So now we can actually find what is, let's call this theta naught, because this is the particular angle which is going to give us the maximum. So we'll call that theta naught. That's the particular angle that gives us the maximum. So that's fine. And so now what do? We evaluate the length, and the length is a divided by the sine. What's the sine? The sine is this over this. So I'm going to write it as a to the 1/3 power divided by the square root of a to the 2/3 plus b to the 2/3. Agreed? That's what that is. Plus, what does this say? B divided by the cosine. What's the cosine? This over this, which is I'll write it as b to the 1/3 divided by, again, the same square root, a to the 2/3 plus b to the 2/3. Now, this just gets the coolest thing in the world. I can flip this up, and it's going to become the square root of a to the 2/3 plus b to the 2/3. That gets flipped up, and then I still have a divided by this. A to the first power divided by a to this is going to be times a to the 2/3 power. And similarly here, flip this one up. I'm going to get this square root, a to the 2/3 plus b to the 2/3. Then that gets flipped up, and I still have b divided by b to the 1/3, which again is b to the 2/3 power. And now notice I can factor that same quantity out of both of them. And once I do that, what am I left with? I'm left with a to the 2/3 plus b to the 2/3, which, look, is exactly the same as this. This is to the 1/2 power, this is to the first power. So when you multiply them together, you're going to get a to the 2/3 plus b to the 2/3, all to the 1/2 plus 1 is 3/2 power. Isn't that just gorgeous? It's just gorgeous. It gives me goosebumps every time I do that problem. So there's the final answer. Look at that for a beautifully symmetric answer. You have a to the 2/3, b to the 2/3, and then you flip it around to the 3/2 power. So now there's a formula. If you had any hallway, all you had to do is take this value and take this value and put them in here, and you're going to be able to find the longest board that can go around that corner. And again, that's assuming the board is super thin. But the fact that it's a little bit thickness, you can probably alter. You can compensate by the fact that you can lift it up a little bit. So anyway, this will actually give you a neat result. So very, very cool. So anyway, so next time we've got 2 more really neat problems, and they're coming up.